Thank you, Colin. Thank you, Peter, and the whole Republic of Ireland chapter of AUSTRALASIAN for the kind invitation to give this guest lecture. I'm the Australian chairman of AUSTRALASIAN as well, so it's lovely to be here in another country giving a lecture to AUSTRALASIAN members and students. As Colin mentioned, one of the things that we've been as a team, Australia-New Zealand team, and I know it's sometimes difficult for people to pick up the accent. I've been in two taxis this afternoon. People thought I was a New Zealander, so but we work very closely with our New Zealand colleagues. So the last 10 years, I've been working with a very close colleague who was from the UK. He's now based in New Zealand, Dr. Stephen Hicks. He works for what's called HERA, the Heavy Engineering Research Association in New Zealand. And we've been working on two major projects. One is the Australasian Bridge Design Guide for Steel and Composite Bridges. And the other one, which I've chaired, is mainly dealing with the use of steel and composite design for building structures. So particularly when you think about all the inherent difficulties using steel in terms of stability and so forth, being able to make some of the elements composite actually makes them more efficient, but also solves a lot of the stability issues, lateral buckling, flexural torsional buckling of columns and so forth. So what I'm going to talk about today is really some of that work in developing the standards and maybe some of the research that has gone on previously to inform the standards. Now, we're not just living in a bubble in the Southern Hemisphere. What we've done when we've developed this standard is we've tried to look at all the best practice in some of the international standards around the world. A lot of the developments in terms of the Eurocode in Europe, and also AISC specifications from North America as well. Now, when I got the invitation to speak, I thought I knew there was a really strong link between Ireland and Sydney. And in fact, one of the most eminent professors and engineers in Australia, Professor Warren, William Henry Warren, he was actually educated at the predecessor of this institution, I think, which was the Royal College of Science, Dublin, I think, which is eventually became part of UCD. So he's very influential in terms of setting up engineering in Australia, particularly in Sydney. Our Melbourne colleagues, University of Melbourne, started civil engineering. They were the first in the country to start civil engineering, but Professor Warren, who came to Australia, he set up engineering. He was the first professor of engineering at the University of Sydney, and he also became the first president of Engineers Australia. And so Colin was talking about the importance of bringing research to practice. I think there's been a strong history, not just at our university, but all the other universities in Australia in doing that. And he wrote a lot of the seminal texts dealing with design of iron, steel and timber, which found their way into some of the very, very early Australian standards. So some of the people that have been involved in these two major projects, as I said, myself, Stephen Hicks, we've co-chaired these two standards. One of my colleagues from the University of Western Sydney, Dr. Kang, he's been working heavily on some of the reliability work that we've carried out as part of the standard. And two postdocs of mine, Dr. Tai and Dr. Aslani, who've also worked on various parts of the standard. So I thought I should acknowledge their contribution up front. The two major standards which I was referring to, Australasian Standards 5100 Part 6 is a revision of an old bridge standard. It deals specifically with steel and composite structures, and ASNZS 2327 is the composite steel and composite bridge code. What I'll try and take you through is a very, very brief history of a more recent history of bridge structures, past, present and future, and really looking at the advances in materials over time, the increases in compressive strengths that we've been able to allow over time through testing, research and so forth, both in bridges and buildings. And then I'll take you through some of the I suppose relevant parts of the standard which slightly different in the areas that we've been concentrating on, and a lot of those areas have really been guided by a need in practice to have guidelines for use of innovative products and concepts. So, as I said before, I mean, with composite construction, one of the issues, particularly for steel, is being able to resolve some of those instability issues. But one of them, old adages for steel and composite structures is really that the overall behaviour is greater than the sum of the parts. So if you link a concrete slab with a steel beam in terms of flexural capacity by providing that longitudinal shear connection, you can get a flexural capacity which is greater than the two elements if you treated them individually. So that's for flexural members. For compression members, and this is a bit of a statistical study that was done by the Council of Tall Buildings and Urban Habitat. They do this every year, and this is also to see how important it is to carry out some of the research that people have been doing into particularly different types of column forms. And one of the things that we've noticed over the last few years is the great shift from concrete frame and steel frame buildings towards composite frame. So this here gives you a bit of a history in terms of building framing going back from the 1930s. You can see dominated by steel. 96% of the tall building frames there were dominated by steel. Moving on to the 80s, you can see the development of high strength concrete, showing an increase in the use of concrete in tall building frames. You can start to see maybe the concrete is stabilising here, but what's really started to now dominate, if we look at steel framing, composite framing, which is obviously steel and concrete together, and mixed is probably also composite. It's now starting to dominate in terms of overall tall buildings. And I think that trend will probably continue. I think you can see a lot of the developments, particularly in places like China, where tall buildings seem to be going up on a weekly basis. Majority of the steel frames, majority of the frames you can see there are predominantly composite frames, and in many cases using concrete fill columns. So some of the developments in our standard, we've tried to keep that in mind, because that's an important concept to make sure that we've got provisions that reflect those needs in industry. So if we go back a little bit to steel and composite bridges in Australia, I mean, if we're going back 50 years, this is one of the major crossings north of Sydney over the Hawkesbury River Bridge, over the Hawkesbury River. You can see here in parallel we've got an old steel truss bridge here, and these are the new steel box girders that were being designed back in the early 70s, and you can see they're being made composite with a concrete deck through the presence of shear connectors. So majority of our standards since then have taken that into account, and particularly with bridges, fatigue provisions for shear connectors have been one of the central issues associated with composite bridge design. If we look at buildings, and that also reflects probably historical nature of construction in Australia. After the Second World War, Australia had a very major infrastructure project. It was the Snowy Mountains hydroelectricity project, which started just after the Second World War. And that was a major project, building a number of hydroelectric dams on the border between New South Wales and Victoria, halfway between Sydney and Melbourne. And as a result of that, there was a large amount of skilled labour, particularly from Europe, that was brought over, and a lot of skills developed in the concrete construction field. At the same time, or probably a decade after that, a lot of the cities, particularly in Sydney, they started to drop some of the height limits that existed. So Sydney had a height limit I'm not sure if some of you may have been there, but there's a place in centre of Sydney called Martin Place, and the bell tower there, the GPO. At one stage there was a limit in terms of tall building heights, that it couldn't exceed the maximum height of the GPO. Now that was lifted in the 60s, and so a lot of developers were looking to develop major infrastructure, tall buildings, and a lot of that was influenced at the time by a lot of the North American development. So you saw in the 60s, the majority of those multi-storey buildings were steel framed. And then as the Snowy Mountains, if you like, projects started to be completed, a lot of those concrete construction companies and the workforce associated with them, they were looking for projects to work on, and they came back to major cities like Sydney and Melbourne. And then you started to see the domination of concrete construction in multi-storey framing throughout the major cities of Australia. So I suppose as a person who's conducted research in steel and composite, we've seen those trends, and working closely with the steel industry, we've certainly suggested to them, if you're trying to come up with alternatives to concrete frame construction, there's got to be quite a bit of innovation. You've got to make your structures somehow more efficient than what you might be able to do with a typical post-tension structure. So you often see continuity in construction becomes important, making things composite, whether they be columns, slabs, beams. All of those elements were used in this first major composite building back in the mid-60s, and based on major steel buildings after that, composite construction has certainly been the rule in many of those cases. So if we just go through a bit of a history of bridge structures, I mean, box girder construction again back in the 70s, using composite action with concrete deck, mainly because of some of the rules that were developed. One of the things that we started to see through over the last few decades is the increased yield strength that we've been able to allow. So we back in the 90s we were able to increase yield strength in steel up to 350 grade, which at the time was quite considerable. We've recently introduced some changes in the steel building standard in 2012 to double that yield strength. So for certain applications you may want to have a higher yield strength, and we've recently, as part of the bridge standard revision, also now allowed sections to be fabricated up to 700 megapascals in yield strength. The other thing that's becoming apparent is the major influence that architecture and urban design has on infrastructure design. So when we were developing the bridge standard, a number of the consultants on bridge standard said, we really have to have methods, we have to have flexibility of methods in the standards, not just prescriptive rules which people will apply in a rote fashion. We need to have a little bit of flexibility to cope with these non-standard designs. Even though there's a certain degree of standardisation, you might be able to see there that when the engineer got involved, the architect originally in this wanted to have the concept of this bridge just floating in space, so they wanted these bubbles in random form, if you like, in the steel section, and when the engineer got involved they wanted to ensure that there was some sort of load path that could be transferred through that, stiffened up the holes. But what we decided to do as a committee is to have a little bit of guidance on, if you were carrying out final element analysis for non-standard structures, what would be important issues that you might need to be considered in the design and the analysis of that bridge. So that was heavily influenced and informed by bridge practitioners as well. If we go to buildings, and in many cases, and I'm sure that the same is true in Ireland and many other places, we have very innovative builders and contractors really stretching the limits in terms of material strengths on construction projects. So if we look at this particular building, which was completed back in 1988, very major tall building on the foreshore in Sydney. The designers decided to use very high strength steel in the columns to try and minimise the footprint of the building in the car park regions. So they were using very high strength steel, 690 grade, and we only managed to actually formulate that into design drive in 2012. So you can see, close to 20 years after the original use, where we developing standards for that. And I think that's going to be true for many cases in the future. You see the very innovative designers and builders really stretching the limit, and then as co-guiders later on we come back and we try and develop standards that might be able to be used more broadly by the industry. So you can see that, I mean, the major reason for doing this, particularly in Sydney, which is founded on very good sandstone. Most major multi-storey buildings in Sydney require, even though government's trying to, if you like, encourage the use of public transport, each building still needs to provide a certain minimum number of car spaces. And because of the very good foundation material in Sydney of sandstone, the excavation costs become very, very expensive. So by trying to minimise the number of car spaces on any level, or maximise the number of car spaces on any level, you can do that by trying to minimise the number of columns in that basement level. So by using much higher strength materials. So these days you see very, very high strength concrete being used. We're stretching that right up to 100 megapascals in our most recent standards. Again, this is another example of very constrained sites in Sydney. Just like any city, I'm sure Dublin has the same issues where with limitations for craneage and so forth, being able to use high strength steel sections becomes quite an important issue, and obviously design standards that reflect that are important. Again, a slight variation of this. I mentioned before when we looked at the Council of Tall Building and Urban Habitat statistics, and this is certainly the case in most of the multi-storey steel buildings that we see in Australia. Most of the builders want to use concrete filled columns for the perimeter frame. So standard is to use concrete lift core for lateral resistance to wind in most cases. Then there's a perimeter frame, and that's generally, if it's going to be a steel floor system, in most cases it's a concrete filled steel solution on the perimeter. This particular building used twin tube arrangement, and the reason for this is to do with the steel supply. In Australia, steel manufacturers only produce up to 508mm diameter, and so in order to maintain a very consistent supply for this and other projects, they use a twin tube arrangement. In other projects, and in more recent projects, what they've been trying to use now is non-standard tubes. So these ones are cold formed. Fabricated steel tubes are now becoming quite common, and being able to be produced in very, very large diameters as well. So I think that's the next. Yeah, so this is the project I was inferring. In this particular project, you can see here, much larger steel tubes are being used. These are spirally welded. So the advantage of being able to spirally weld tubes is you can manufacture tubes at much larger diameter. So it's quite typical to manufacture these up to 3 metres in diameter. That's quite a popular method of manufacture for steel tubes for very tall buildings. It's also being used a lot for the fabrication of the towers for wind turbines, which again are being used for renewable energy in many parts of Australia. And so we had a dilemma originally. We didn't have rules for spirally welded tubes and for that method of manufacture. So again, that's informed some of the research that we've been able to carry out as part of the revisions of the standard. Another important issue, and I think this is probably reflective right around the world. I mean, this is a project which was originally completed in 1988. It's a major convention centre in Sydney. So the New South Wales government wanted to basically knock this particular building down, take out all the steelwork, maintain the original concrete plinth which had car parks and services and so forth, and all the foundations in place, and then build a new steel structure on top of that. So that's just been completed, the new Sydney Convention and Exhibition Centre. I just visited it late last year, so there's some very, very long span trusses in there, and very, very large columns. These are about 2 metres in diameter. Now the major issue, one of the major issues on this particular project and many other projects that we're now seeing in Australia is many of the fabricators and steel suppliers are just not able to keep up with the complexity of the steel work that is being required of these projects. So in this particular project, there were 2 major overseas fabricators. One was South Korean based, and the other was based in China. So the builders decided to go down this path of using foreign fabricators. But what they then put in place is to ensure that they had a very, very strict regime to inspect the steel. They employed Bureau Veritas inspectors on both sites to ensure that the supply of the steel was able to be supplied to relevant Australian standards. So we're starting to see that on major projects. So as a result of that, what we've been doing, particularly with our New Zealand colleagues, is to look at the effects of the use of imported steel. Does that have any influence on particularly the design approaches that we use? One of the issues is if the steel is supplied to a particular relevant Australian or New Zealand standard, can we ensure its safety in terms of the capacity? So we've done some work on that. I'll talk about it a little bit later. But this is a common issue because a number of the major projects, particularly these very large infrastructure projects, have used a lot of imported steel. So this is, again, I was speaking to the cab driver on the way over. He said to be quite had an interest in lots of sports. This is Randwick Racecourse, Royal Randwick Racecourse, for those of you who follow the horses around the world. So this had a very major upgrade a few years ago. Again, using a lot of imported steel. So all the new roof in this particular structure was all imported. And that's the stadia here on the right. So I'll now try and take you through a few of the nuts and bolts of the standard. Just some of the elements which I think are probably worth highlighting, and I've tried to focus on some of those in the prelude. So this is the draft bridge standard 5100 Part 6, which should be, in fact there's a major launch in Melbourne when I get back. Colin might be aware this is AUSTRALASIAN conference which happens every 2 years, so there's a major launch of this in, I think it's April in Melbourne, where each of the standards, there's I think 10 parts of this standard which will be released. So the elements of this which are worthwhile highlighting, we've had a series of gradual increases in concrete compressive strengths over a number of years, and so what we've done in this new standard We've tried to keep this in parallel with our concrete standard, AS3600, and the most recent revision of that was in 2009. And so now we're able to produce and produce guidelines to design for concrete compressive strength, characteristic ones, up to 100 megapascals. So for bridges, I suppose that would be important, particularly things like bridge piers and so forth, where you're trying to get very large compressive strength to minimise pier diameters and so forth. But it's also important in terms of construction practices, being able to get high early strength for slabs and so forth, and in some cases using concrete compressive strength in slabs on bridge girders or bridge sections up to 100 MPa is not that uncommon. Now we also have, well, our limitation on reinforcing yield strength at the moment is 500 megapascals, but I know there's some ongoing work, particularly in the concrete specification, to increase that based on some recent research. I mentioned before the increase up to 690 megapascals, which is a Queensland tempered steel. So there's been a lot of ongoing research, both at University of Sydney, where I am now, but at the University of Western Sydney and Wollongong, where we had teams working on that over a number of years. So 2012, there was a major amendment to the Australian steel setting AS4100 to allow for design rules up to 690, and we've ensured that the bridge standard has enabled that increase in strength as well. It's not as straightforward because our AS4100 is an ultimate limit state standard in terms of strength. The bridge standard is, I suppose, somewhere between an ultimate limit state and also a permissible stress state, so that in some of the areas of design, even though we're able to allow up to 690 grade, you don't get the full benefits of using that. So issues associated with fatigue and so forth, you'll see limitations on what strength you may be able to use. So, I mean, if we're looking at strength and if you're able to get a composite girder to be designed with high strength steel for strength alone, you could take advantage of high strength steel, but we've got some reductions in there to allow for the fact that we don't get full yielding throughout the depth of the steel beam, and we make allowances for that, as we do in the building standard as well. So as I mentioned, one of the key things in increasing the compressive strength up to 100 MPa for bridge girders, how do we make them composite? So what we have to do is we have to go back and look at all the particularly all the test data that has been carried out on shear connectors for connecting concrete slabs and steel beams, and this is a lot of the work that was led by Stephen Hicks and his group, and we carried out a whole series of reliability studies. So we were able to show that we could at least up to 80 megapascals validate that all the existing design rules for shear connector capacity were valid, and we made some appropriate changes to the capacity factors for that particular mode of failure. So these are our two strength equations for shear connectors, which is probably very similar to the ones that you have in Eurocode. The first one there is basically fracture of the shear connector, which is primarily based on the ultimate capacity of the steel. It's basically a shear failure of the shank. And the second one there is a concrete failure, where we get a concrete cone around the shear connector failure. It's predominantly affected by the compressive strength and the elastic modulus of the material. These are empirical equations which have been developed many years ago. So one of the other elements which I mentioned before is this whole issue of foreign supply of steel. It is very important, particularly for our New Zealand neighbours who don't have a major manufacturing of steel. It's very important for us in Australia as well because we do actually import quite a bit of steel, so we think it's an international issue, and obviously we're trying to overcome those barriers of trade in terms of material, whether it be steel or any other material for that matter. So what we did, we looked at what we call the delivery standards for manufacture. Some of you are probably familiar with this, and there's a number of, if you like, areas that we split it into. The Euro norm, EN, has the Korean steel suppliers all supplied to the Euro norm. There's the JIS, which is the Japanese standards, ASTM, ASNZS, which is our own Australia and New Zealand, and then we also looked at the Chinese standards as well, GBT. We've pretty much covered what we think for the entire world in terms of delivery standards, and so these are just the tolerances that each of those standards would supply to. So what we wanted to look at is, with those different tolerances, if we accept material into Australia and New Zealand with these different delivery standards, how does that affect the existing design equations that we have for strength and so forth? Do we have to be alarmed? So we looked at 3 cases for bending, what we call compact, not compact and non-compact. So initially what we're looking at here, there's a number of parameters that we're looking at. The first thing to look at here is the capacity factor on the vertical axis here. Sorry if this is not that clear. On the horizontal axis there is our reliability index. So our reliability index for Australian standards has been calibrated to about 3.0, which is just about there. This third line there. And what we also had is there's a third parameter in there, the coefficient of variation of the yield stress of the material. And we varied that from 5 right up to 30. And now if you look at the joint structural standard, which I think most European codes have been calibrated to, coefficient of variation of yield stress is about 7%. We don't actually stipulate in the Australian New Zealand standards what that variation should be. My colleagues and I think if we set it to not be greater than 10%, and you can see by the results that we have here, by doing that we would maintain our reliability index of 3 and above, and we would also maintain a capacity factor of 0.9 and above. So we could come at this from a number of ways. We could either put a limit on the coefficient of variation of yield stress, or if you had a higher variation of yield stress, say a particular supplier somewhere around the world had that, then they would have to downrate their capacity factor for design. So that allows that flexibility. But if we kept those other 2 limits constant, coefficient of variation of yield strength and reliability index, what we found is that the capacity factor, the existing capacity factor is 0.9 for steel, and that was calibrated to all the steel that was used in the existing Australian standard. We found that from all the delivery locations around the world, we would be able to maintain capacity factor of at least 0.94. So in that case, there was no cause for alarm, even though there may be some parts of the industry that thought there was. What we wanted to really look at this from a scientific level. Is there anything to be alarmed about if we ensure that fabricators and suppliers from around the world supply to what they said they have, then our existing standard would be suitable, and designers and engineers would have confidence in the use of the design standard. So that was an important initiative. We did some other reliability studies, particularly in relation to concrete filled columns. In the past we had some fairly heavy penalties for the capacity factor for concrete in compression. Our capacity factor for steel in compression we were happy with. It was about 0.9. This one was as low as 0.6. So as a result of some of the work that we've been able to do, and this has also been reflected more recently in some of the reliability work that they've been doing for the revision of the concrete standard, we've been able to look at improving this capacity factor here. Now for composite, there's a number of reasons for that. We also get confinement for concrete filled columns. We also find that heterogeneous shrinkage is lower in concrete filled columns, and so that ends up resulting in a higher compressive strength. But we've been able to show that if we kept the capacity factor for steel constant at 0.9, that our capacity factor for concrete could be as high as 0.7 in some cases. We've looked at this for both rectangular, circular columns, both for short and for slender columns, taking into account issues associated with buckling and so forth. So we've made some suggested revisions there, and typically we'd be using a sliding factor for capacity factor of concrete and compression above 0.6 of what it used to be. So moving on just to the draft standard for composite buildings. Some of the issues that we, because these two studies these two standards were developed in parallel, some of the material is, if you like, consistent. Just in terms of the outline of the standard, previously in our 2003 version of the standard, we only really covered composite beams. Now we cover composite slabs with metal decking. We've got a section in there on composite columns, concrete filled columns and encased columns, design of composite joints. But these two sections here are quite new, and these are really trying to deal with system behaviour. So particularly for composite beams, systems in floors, taking into account the three-dimensional nature of the floor system for serviceability and vibration, we thought was quite important, and that allows for a much more efficient design looking at those serviceability issues. Likewise for fire resistance, being able to take into account, and we had a tiered approach. We've got a series of design approaches for looking at individual elements for fire resistance, but also looking at system behaviour. Once again, acknowledging that steel, when you look at fire situations, unless you're taking into account that system behaviour, it can be quite to be a system that's heavily penalised in fire resistance. Now, the final section here is on earthquake. This was led primarily by our New Zealand colleagues, but there are situations where in Australia, in particular regions, where you may actually have to use this section, particularly in places like Adelaide. Adelaide in Australia has much higher seismicity than other parts of Australia, and also has poor quality soil. So you'll find a lot of steel buildings, composite buildings in that city tend to have to have that higher tiered approach for earthquake design. So just going through some of the issues, one of the issues that, and this was actually led by one of my colleagues in the University of Sydney, and this is a phenomenon that we looked at quite a number of years ago. So if you look at a traditional concrete slab, you've got a free surface here which is exposed to the atmosphere. Let's assume you don't have the decking here, and it's a concrete slab. Again, you've got this bottom surface that's exposed to the atmosphere. You get, if you like, moisture travelling out at the top and the bottom of the slab. When you look at shrinkage, free shrinkage in a concrete slab, you should actually have a constant shrinkage value throughout the entire depth. Now the problem that arises when we have metal decking is we get the moisture loss through the top, there's zero moisture loss through the bottom. So what John Leake has been able to find is that we actually get this non-uniform shrinkage throughout the depth of the slab, and what this ends up doing, many people thought originally, certainly when we look at concrete filled columns, there's a beneficial effect. But when we're looking at composite slabs, it's actually a detrimental effect, because you get high shrinkage at the top, low shrinkage at the bottom, you get a net, if you like, moment which is actually going to increase the deflections in the slab. So in fact this work was originally funded by the decking industry. They weren't entirely happy with the outcome, But the reality is we've got to reflect what actually happened. And so a lot of the software manufacturers, the software developers that incorporate all these rules in their software packages, they've now incorporated this effect. There are ways to overcome it if you were designers. Some ways that builders might be able to overcome this is to have some sort of membrane that you place on the top. You can try and minimise this effect. But that's one of the issues that we've tried to incorporate in this standard. I know John Luke is on a number of the TC committees, and they've also been trying to see about revisions for the Eurocode in the next few variations. So there's a very simple model for trying to take this into account in there. Some of the other issues, again, I won't go over this. We've now allowed for high strength steel for composite buildings as well. One of the areas that I've worked closely with one of my colleagues, who's an ex-postdoc of mine, he now works at Heriot Watt University in Scotland. But we did quite a number of, we did a few fairly large experimental programs, but also some numerical analysis. The key issue here is primarily, when we're looking at shear strength for composite beams, we always used to rely entirely on the shear capacity being resisted through the web of the steel beam. And most people recognise that there is a contribution that the slab does resist, particularly obviously if we've got it connected through longitudinal shear connection. And we've been able to come up with an expression and a way for evaluating that, if you like, that additional shear capacity. It can be up to 15% capacity it can develop, somewhere between 5 to 15%, depending on the span situation. And so that's a new area that we've incorporated this into. And again, George has been working with, I think, Professor Johnson at Warwick University, and they've been looking at trying to maybe influence Eurocode 4 for the next revision to incorporate this work as well. Columns, I mentioned before. One of my colleagues at the University of Western Sydney was also working on a number of areas associated with looking at bond. We looked at the original bond shear strength models, both in Eurocode 4 and some of the other standards around the world that were quite limiting. So we've been able, through some new experimental research, to broaden the types of cross sections that we can develop shear strength in. So once we exceed this shear strength for a column, what we're then trying to rely on is the additional shear capacity to be transferred through maybe longitudinal shear connectors or some sort of other mechanical shear connection. The other issue that's important here, and this is when we developed some of the work on the benefits associated with concrete inside a steel tube for local buckling. In fact, the AISC specification they were making some changes to their standard. So myself and also my colleague Mark Bradford have done some work on steel tubes to look at the increased D/T ratios you could develop for the concrete filled steel tubes. So we actually we originally worked with the AISC to modify their specification, and those exact rules we've incorporated back into our standard. So now we've got increased width to thickness ratios for rectangular hollow sections as well as circular hollow sections. So originally we developed it for axial compression, and the Americans had extended it for members in flexure as well. I think I mentioned before the work that we've done on spiral welded tubes. Now this is an important development because, as I said, this is really what industry is wanting. Most of the concrete filled, most of the steel frame buildings using concrete filled columns are using this method of construction, and so a number of our rules in the new standard have been able to provide rules for that method of construction. And there's not too many changes. The key issue is with this type of material when it's spirally welded, the material strength both parallel and perpendicular to the direction of rolling can be quite different. And so in design, when we're designing for this axis here, we need to make sure that the material properties are in parallel to the direction of loading. So they're the major changes that we've made in that respect. As I said, some rules on composite joints. One of the areas that Dr. Ty's been working on, we've looked at some of the Eurocode 4 and 3 models for steel and composite joints, and there wasn't actually a model in there for concrete fill columns, so we've adapted the existing models from Eurocode 3 and 4 to be able to be used for concrete fill columns, because actually most of the design scenarios in Australia, we do actually have concrete fill columns as a major column element, and so we've adapted those rules to now allow for that particular method. So we've got a stiffness model for looking at rotational stiffness and also moment resistance, looking at strength of the joints. I mentioned before the section on composite floor systems, and again this has been heavily driven by Dr. Ramsey and Dr. Hicks from HERA, looking at so the way the whole system behaves for long-term deflections and also for vibration. So we treated the entire floor as a series of single members. We're not getting that beneficial effect that comes about by having secondary beams and the entire slab assisting in trying to resist deflections and vibrations. So that's a fairly important section. Likewise for fire resistance, we've incorporated rules for the panel method for composite buildings. Some of you are obviously familiar with this, where the system is if you protect the primary beams and you leave the steel beam, the secondary beams unprotected, that allows the steel beams to significantly deform. You get catenary reaction developing in the panels, and that's a controlled method that you can use, which is quite efficient for the fire design of a steel and composite floor. So that's an important, again, another important section in trying to make steel systems efficient for design, because those are the two areas where it probably is heavily penalising existing rules, serviceability and fire resistance. I mentioned design for earthquake. So I don't have time to go through everything here, but as I said, there is a imperative obviously for our New Zealand colleagues, and when we started doing this work shortly after the Christchurch earthquake. So there's a lot of existing and ongoing research in New Zealand. A lot of that is heavily has guided this section. So they had a whole team working on this. It was headed by Kevin Cowrie from Steel Construction New Zealand, people like Charles Clifton and Greg McRae, who both from University of Auckland and Christchurch University have been working on this. Again, they've been looking at existing methods, particularly from North America, and trying to incorporate those in this standard. And as I said, depending on what scenario we have in Australia, we either go into this section or we don't actually have to design for earthquake at all. What it's suggesting is the existing provisions in all the sections previous to that are sufficient, and we don't actually have to go any further. But okay, so I'll just conclude there. I suppose what I've really tried to focus on is some of the, I'll pick out some of the areas of our standard which I think are probably slightly unique. I suppose any international standards organisation, as they're going through that development, would like to pick up the best practice throughout the world and also incorporate some of the areas that we've carried out research in. I think that's what we've done, and obviously there's a timeline. We could actually add more, and there's a timeline. That timeline has probably been well exceeded, but we're hoping this standard will be out well, actually, we've got public review comments for this that we've dealt with. We've already got over 200 comments. We complete those in March. The building standard will be published probably around about July this year, and the bridge standard is going to be completed and published in about April or May. So, yeah, I'll stop there. Happy to take any questions, and likewise, if anyone wants to email me, feel free to. I'm happy to provide people with draft versions of these standards because they're open for public comment. We've actually had people public comment on this, even though they were from international organisations, and I'll be more than happy to share that with you. So, thank you very much for your time, and yeah, happy to answer any questions.
Thanks, Brian, for a very interesting presentation. I'm Alan O'Connor from Trinity College. I'm interested to hear what you said about the target reliability levels which are used to calibrate the code.
Yes.
And one of the things which interested me was the fact that with the target reliability 3.04, that gives a probability of failure which is about an order of magnitude higher than that which the Eurocode allows. So I wonder if you comment on that, and also in this new document, this bridge design code, do you allow reliability-based design?
Yes, we do. So, I mean, the short answer to the first part is that, I mean, that's the historical nature of AS 4100, 3600. So we've always had that target reliability for members. If we're looking at connections, it's even higher. So what we've tried to do is keep consistent with that. We do have a whole section in the standard for, and it probably exists there for people who want to develop their own products, or they want to do a more advanced reliability study. So we've got our Australian standard, I think it's 5104, which is basically complete reproduction of the ISO standard for reliability. So, and I realise that that's just currently going through a revision as well. So we've allowed that as an alternative method of trying to satisfy reliability of your structure or your component that you might be designing to be part of the standard. So yeah, I don't know if that answers your question.
That's great. And do you, in addition to this specification for the design of bridges, is there a parallel specification for assessment of structures which also... Oh yes,
absolutely, yes. In fact, I was involved in that. We've got two others. So this is just dealing specifically with steel and composite bridges. So there's 10 parts now. So this is part 6. Part 7 is a section called rating. So it deals with, and I can provide these to you if you like. There was the new section that we introduced, which is essentially rehabilitation. So actually those three parts are quite, there's a lot of crossover between those. And then part 2 also deals with loading, where you've got the reliability aspects of the loading side of the bridge design as well. And then 5 is part deals with concrete structures. There's a new part on timber structures, which is part 10. So yeah, but this is the only part which is really Australia and New Zealand specific. All the other parts are just Australian standards per se. Yeah.
Thank you.
Yeah.
Thanks for talk, Brian. Just a question in relation to the serviceability criteria, and obviously the research. Is that considered a sort of long-term serviceability stage in terms of, say, creep within the concrete and composite slabs and concrete beams, cracking, is typically a problem with constant construction and vibration, in the long-term issue?
Yeah, that's true. So in section 4 of the standard, we cover sort of long-term deflections, dealing with creep, shrinkage. I mean, I talked specifically about that shrinkage aspect associated with composite slabs, but yeah, we've got provisions in there for how we deal with shrinkage, creep, and vibration is really dealt with in that system behaviour part. So,
and is that usually locally? Is there something as crude as that, or is it much more involved in looking at response factors?
Yeah, so I think that was heavily influenced by Stephen's work at SCI. So they developed a design guide there. So That's one of the appendices of the standard. But it doesn't preclude you from using any other method. It's just that we've provided some guidelines, and they're not prescriptive. We've got two parts of the standard called informative and normative. Normative is what you must use, and these sections we've probably made, particularly serviceability, is quite subjective, so we've made those parts informative, so to speak. And the limits are even informative.
Really?
So it's really up to the, yeah.
Informative life then is key.
Yeah, we spent a lot of time debating this actually, because a number of us on the committee wanted to make these normative, but then what we wanted to do is, so it's all about not trying to penalise one system versus the other. So we looked at what had traditionally been used in concrete, steel, composite structures. In fact, if we go through all those standards, they're all been informative. So we tried to make this consistent. But you also mentioned, you touched on something regarding crack control. Both when we were developing the rules for the composite bridges and also for buildings, we found the crack control provisions in composite structures were quite different from some of the concrete structures, crack provisions. And for many cases, there were no real, I mean, you could argue that in concrete structures there may be more restraint for, maybe a beam and slab type of system. But we've tried to ensure that there's, at least some clarity there and some uniformity in those crack control provisions. So in some cases, we've just referred those crack control provisions off to the relevant concrete standard in the two countries. Yep.
Tom? Brian, probably a bit of a loaded question maybe, but you've obviously got a huge experience in code development across many different codes. Would you kindly comment on the interplay between research academics who want to see their research become used,
yep,
industry that has vested interests in particular products and so on,
yes,
and who's the referee?
It's good. That's a good question. I've had to deal with a lot of those issues over the last 5 years. If I start with the whole issue of, academics wanting to see their work. I mean, some of the areas of work which we've seen go in the standard. I mean, if I just take areas that I know that we've been involved with, and I had a discussion with people in the medical field about this as well. Some of the areas that we've done work on were 15, 20 years ago. We've now finally seen some of those rules change in the standard, and that's certainly quite similar time length to the medical field, where you do trials in the lab, and by the time they get approved through the various approving bodies for drugs, 15, 20 year gestation period is not uncommon for the medical field as well. So, I mean, in terms of academics getting involved in standards development, I think, there could be a certain degree of wanting to see your own work be utilised. I mean, there's quite a number of things that we've done in terms of combined actions, which in composite members, which I think, there's probably not that much of a need for it to go in just yet. We've done the work, but maybe in the next revision. So, but I think it's important for if you're talking about the academic community to be involved in it, just to see how the process works, and it may not be just to get your research included in the next revision of the standard, but just to see how and to see what industry sees as important as part of that design development stage. In terms of vested interests, that's a hard one. I mean, most standards bodies do have code. There's a stipulation for how many people need to be represented on different committees, and getting that balance of committee, ensuring there's no conflict of interest. That's a really difficult one. Look, I think standards probably could do better on that. I mean, I suppose a number of things that I've seen over a number of years that really frustrate me. My view is there probably should be some sort of ombudsman there to try and weed out some of these things, because I think they affect the industry and the community at the end of the day, because if there's too much vested interest in there, at the end of the day, I think the science should prevail. If people show that with the science that it's safe to use products or concepts or materials, then that should prevail, and that should be above that vested interest. And quite often, you get frustrated well, I've been frustrated, probably not as the chairman, but certainly as a committee of one of the committees that I've sat on for the last 5 years by what I would see that perceived, so that conflict of interest. Maybe not feeling that it was adequately dealt with, but at the end of the day, it's really up to the standards body to ensure that that is maintained. It should be more than just a box ticking exercise to say I've got no conflict. I think if it is perceived that there may be a conflict, maybe there should be some independent body to actually look at that. But yeah, so I mean that's probably my personal view of things. Yeah, at the end of the day, I mean it's a matter of whether you want to really fight those battles or maybe see it changed in the next revision of the standard or so forth.
Yeah. Yeah, thanks Brian for a great answer. And question, Peter, you show a picture of a non-standard structure, a beam with various bubbles in it, holes in it, and you made a note that you now included some provision in the code for non-standard structures, and I wonder how do you go about that, and you mentioned you had to find analysis guidelines, but I just wondering what is the general contents of the non-standard structures notes in the code?
Yeah, I mean I think every standard has, every building code has this, as long as you've got an alternate pathway. I suppose what we wanted to do in this section of the bridge standards, perhaps not give guidelines for how you would carry out finite element analysis, but if you're going to do some other non-standard analysis, what are the important issues to take into account? I mean, most of these should be obvious. You've got to look at method of manufacture, how you quantify imperfections, residual stresses, those types of issues, and maybe provide enough guidance for engineers to maybe find out or be directed to the right literature to be able to quantify those things. So we weren't trying to be too prescriptive, but maybe just give some guidance, and it's probably at the end of the day it's only about a page, and there was an attempt, and Colin might know this one, there's a group in Australia, Engineers Australia guideline put out on how you conduct finite element analysis. It was only 20 pages long, but I think the document ended up costing people, if they wanted to buy it, well over a few $100s. But my view is that it wasn't a very useful document, 20-page document with something that's much too prescriptive. I don't think it's going to really be helpful. I think you have to leave it up to the experience of the engineers and their colleagues in the office. All we can do is provide a little bit of guidance. We're only just trying to touch the surface on what we think is what are key issues, and then we leave the rest up to the designers, because I think there's enough experience there without having, and we see this with a lot of the standards. I think certainly for the building standards, and this also was a bit frustrating from my perspective, sometimes you get the feeling that there's a number of people on the standard that just want everything written into some prescriptive rule, but when you look at a lot of the consultants out there, they're not constrained by that. Maybe it's the small to mid level consultants that might find that type of document more useful than the larger consultants that have got a lot of expertise, that are willing to try and almost do their own research in-house to develop rules with enough experience and confidence. So yeah, it's always a balance. I think it's useful to develop a document, but it's also, I feel, useful to ensure there's enough flexibility there that people can maybe use some elements of the standard, but definitely go off and do their own independent work and use their own in-house expertise and knowledge. So yeah.
kind of metal decking, and I'm kind of chasing my tail a little bit because I've got a beam depth which might be too big to actually engage with the shear connectors to engage the sort of the effective width of the slab.
Yes.
But if I'm decreasing the depth of the beam to engage it, then sometimes I'm not getting enough moment capacity. So is there a bit of like a happy medium, I suppose?
Yeah, that's true. I mean, the larger the beam depth, the less as a percentage flexural increase you would get, I suppose. Yeah. Yes, I mean, like I say, with some of that work that we did on increased shear capacity, the larger the beam depth, the less that capacity increase would be. So, I suppose, yeah, that's a good question to ask. I mean, but then do you want that shear connection there just to provide lateral stability for your system later on? I mean, that could be a separate question you might ask. You might only be getting 10% additional shear capacity, but does that shear connection then provide you with a much more stable structure during, maybe not during construction, but during the in situ phase? So, but you may then choose to ignore it for the additional strength design or so forth. Yeah, I don't know if that answers your. So what I'm quite often saying is composite action is also providing all those other secondary types of stability issues as well. I don't know if that's the case in your design.
No, it does, but it's just in terms of
Yeah. I mean, one thing we also really struggled with is people wanted us to provide guidance on when you attach the metal decking during construction. You know, how do you quantify that? You know, that stability benefit that you get. We tried to steer away from that because, you know, tack welding the decking to the steel beam, we didn't want to provide guidance that's too prescriptive there. But I know, you know, designers will obviously use that without having to have additional secondary structure there during the erection phase. So yeah, but no, I agree with you. You know, when you get to very large depth structures, the enhancement there may not be worth the additional design effort, so to speak. Yeah.
There's no more questions. Colin, Eugene, give a round of thanks, please.
Well, it's a tradition in the institution that somebody proposes a vote of thanks for me. I've been an academic for a lot of years. When I was first starting out, I went into Prof and I said, what do I need to do to be successful in this business? And he said, there's 3 things you need to do. I'm sure you've often heard it. And you need to do research, and research. And you need to publish, and publish. So it's kind of refreshing now to see that we've kind of moved on a little bit. Some of us are still trying to publish a lot of papers and celebrating large numbers of papers. But it's good to see a bit of an emphasis on impact and moving on, making sure that something happens from this publication. It's also interesting to see the focus on globalization. I mean, the world is getting smaller. I know the bridge over the Liffey, one of the more recent bridges over the Liffey, the Calatrava Bridge, was made in Rotterdam and shipped over. The steel and the fourth bridge in Scotland was made in China and shipped over. More and more this is happening, so your steel might be coming from a completely different jurisdiction. And it's great to see that the new code is starting to recognise that. It's very refreshing. Also going back to fundamental principles, you know, of safety. So the bottom line is you want your structure to be safe, so you want reliability to be a certain level, which is essentially the probability of failure should be acceptable. So you were built up a lot before you came, and we heard that this is a very impressive guy. He's been head of several big engineering departments in Australia. So it's kind of reassuring, to be honest, to find that you set out for Newstead this evening and ended up in Janmina.
Oh, sorry.
So before you leave, we're going to present you with a map of UCD.
Okay.